the multiplication rules, and conditional probability. First, multiplication rule. Statista Motors builds two models of cars, the Regressa and the Devion. 70% of the company's customers purchase the Regressa and 30% purchase the Devion. Floor mats are standard equipment, and customers must select between two different styles, the all-weather mats and the no-weather mats. Previous experience shows that both styles are equally likely to be selected, regardless of the vehicle that was purchased. If a customer is selected at random, find the probability that a Regressa with all-weather floor mats was purchased. Two events A and B are independent events if the fact that A occurs does not affect the probability of B occurring. We are told that both types of mats are equally likely to be selected regardless of which model is purchased, so the probability that an all-weather mat will be selected is 0.5. This also means that the conditional probability, the probability that all-weather mats would be selected given the customer purchased a Regressa, is also equal to 0.5. Likewise is the probability that all weather mats will be selected given the customer purchased a Devion is also equal to 0.5. These probabilities being equal shows the independence between the vehicle model choice and the type of floor mat choice. When two events A and B are independent, the probability that both events A and B will occur is equal to the probability that event A will occur times the probability that event B will occur. This concept is frequently illustrated using a probability tree. When a vehicle is purchased, the Statista Motors customer must first choose between a Regressa and a Devion. Once the vehicle is chosen, the customer must choose between the all-weather floor mats and the no-weather floor mats. He must make this choice whether he purchases a Regressa or a Devion. Now let's assign probabilities to each branch of the tree. We are told that 70% of the vehicles sold by the company are Regressa models. So the probability that a randomly selected customer purchases a Regressa is 0.70. Now, using the concept of the complementary probability, the probability that the customer would purchase a Devion is 0.30. Since the floor mat choice is independent of vehicle model selection, and both floor mat types are equally likely to be selected, the probabilities along each branch in this part of the tree would be 0.50. Now, let's assign symbols to represent the events. This will simplify the process of expressing probabilities. We can let R represent the event that a Regressa is purchased, D can represent the event that a Devion is purchased, A can represent that the all-weather mats are chosen, and N that no-weather mats are chosen. The original question was, if a customer is selected at random, find the probability that a Regressa with all-weather floor mats was purchased. Recall that for independent events A and B, the probability that both events A and B will occur is equal to the product of the probabilities that each will occur. The probability that a Regressa with all-weather floor mats was purchased would be expressed in probability notation as the probability that both events R and A will occur, which is found by multiplying the probability that event R will occur by the probability that event A will occur. Notice that this is basically the top branch of the tree. So we have 0.70 times 0.5 for a total probability of 0.35. So the probability for the top branch of this probability tree is 0.35. Now, let's find the probability that a randomly selected customer would purchase a Regressa with no weather mats. In probability notation, we have the probability that both events R and N would occur equal to the probability that event R would occur times the probability that event N would occur. This would then be 0.7 times 0.5 equal to, again, 0.35. So the next branch down would also have a probability of 0.35. Continuing this way, we have the probability that the customer would purchase a Devion with all weather mats is equal to 0.15. And the probability that a Devion with no weather mats will be purchased will also be 0.15. The sum of all branch probabilities will always be equal to 1. This makes sense since a Statista Motors customer is certain to follow one of these sequences of events. Second multiplication rule. Statista Motors builds two models of cars, the Regressa and the Devion. 70% of the company's customers purchase the Regressa and 30% purchase the Devion. In an effort to increase revenue, the company has recently changed the floor mat policy so that the floor mats are no longer standard equipment. Since the policy change, the company has found that 20% of those who purchase a Regressa also order floor mats. They have also found that 60% of those who purchase a Devion also order floor mats. The marketing manager would like to determine the probability that a randomly selected customer will purchase a Devion with floor mats. According to the given information, the probability that a randomly selected customer would purchase floor mats given a Regressa model was chosen is equal to 0.2, and the probability that floor mats would be purchased given that a Devion model is chosen is equal to 0.6. From this, we can see that whether or not a customer purchases floor mats is dependent on which model is chosen. The multiplication rule for dependent events tells us that for dependent events A and B, the probability that events A and B will occur is equal to the probability that event A will occur times the probability that event B will occur, given that event A has already occurred. In order to simplify the probability notation, let's assign symbols to the events. So let R represent the event that a randomly selected customer purchases a Regressa, and let D represent the event that a Devion was purchased. F will be the event that floor mats are purchased, and NF will be the event that no floor mats were purchased. We were asked to find the probability that a randomly selected customer will purchase a Devion with floor mats. So we will express in probability notation that the probability that events D and F will both occur. According to the formula, this will be calculated as the probability that event D will occur times the probability that event F will occur, given that D has already occurred. This then will be 0.3 times 0.6, which gives us 0.18. Let's go ahead and follow along with your notes now. Let's go ahead and find the probability of compound events using the multiplication rules. Multiplication rules can be used to find the probability of two or more events that occur in sequence. The events are independent if the probability of the second is not changed by the occurrence of the first event. Two events, A and B, are independent if the fact that event A occurs does not affect the probability of B occurring. For instance, rolling a die, getting a 5, then rolling the die again and getting a 3. Just because I roll a 5 in the first roll has no effect on the fact that if I get a 3 in the second roll. Drawing a card, getting a queen, replacing the card, very important, then drawing a second card and also getting a queen. By replacing the card, the second selection is also from the entire deck. meaning that pulling the first card and getting a queen has no effect on the probability of getting a second queen if you replace the card. When two events are independent, the probability of both occurring is found as follows. The probability of event A and event B both occurring will be probability of A times probability of B in the event that they are independent. This rule can be extended to 3 or more independent events. Let's look at using the multiplication rule with large populations and small samples. If we were to have a small sample selected from a large population and the subjects are not replaced, usually that would indicate a dependent event. But here, the probability of the event occurring will change so slightly that, for the most part, it is considered to remain the same, even though the events are not truly independent. For example, if 24% of American consumers prefer a particular brand, then if we choose 2 Americans out of over 300 million and we don't replace them back into the population, the probability that both prefer the stated brand will be the probability that the first American prefers brand times the probability that the second American prefers the same brand, which would simply be 0.24 times 0.24. Let's look at another example. Probability with replacement. Whenever you see the words with replacement, you're pretty much guaranteed that you're dealing with independent events. A jar holds 5 red marbles, 3 green marbles, and 7 blue marbles. One marble is selected and its color is noted. Then, very important, it is replaced back into the jar. A second marble is then selected and then its color is noted. Find the probability for each of the following, starting with selecting 2 green marbles. Then we'll do selecting a blue marble, replacing it, then selecting a green one. Then finally, we will do 3 where we select a red marble, replace it, then a blue one, replace that, then a green marble. Let's first look at selecting 2 green marbles. Since we are taking one marble out and then replacing it back into the jar, we will have the following probability that we actually select 2 green marbles with replacement. The probability that the first marble is green is 3 out of 15 because there are 3 green marbles out of a total of 15 marbles. And then when you replace the green marble back into the jar and then go ahead and select a second marble, the probability that the second marble is also green is again 3 out of 15. Of course, we want to simplify this, and we end up with 0.04. The probability of selecting a blue marble, then a green one now. So once again, we notice that if we select a blue marble, it's going to be out of 15, and in particular, 7 out of 15. With this marble out of the jar, there are now only 14 marbles in the jar. However, since we are replacing the blue marble back into the jar, we still have 15 marbles in the jar. So the probability of pulling out a green marble is now 3 out of 15. Multiplying these two probabilities, reducing, we end up with 0.0933. The probability of selecting a red, then a blue, then a green, again with replacement, so each probability should be out of 15, will be 5 out of 15 for the red, 7 out of 15 for the blue, and 3 out of 15 for the green. giving us 0.0311. Dependent events. When the income or occurrence of the first event affects the outcome or occurrence of the second event in such a way that the probability is changed, the events are dependent events. Let's do an example. Let's determine which events are independent and which ones are dependent. Are the events of having a large shoe size and the second event of having a high IQ independent or dependent? Now clearly, there is no scientific evidence to show that there is a tie between the two. Therefore, these are independent events. A parent being left-handed and a child who is also left-handed. Well, clearly, the parent will have some influence on the genetics of a child. Therefore, we have dependent events. Getting a raise in salary and purchasing a new car. Now, these certainly will cause you to have dependence on one or the other. Obviously, when someone gets a raise in salary, they tend to want to purchase new things. A new car could be one of them. And finally, rolling a die and tossing a coin are clearly independent of each other. The probability of me rolling a 5 and then flipping a coin to get heads clearly have no influence on one another. Conditional probability. The conditional probability of event B in relationship to an event A is the probability that event B occurs after A has already occurred. The conditional probability of event B, given that event A has already occurred, is denoted by the following notation. That is, this is the probability of event B, given that event A has already occurred. The vertical line that you see in this notation means given that. For instance, if an ace has already been drawn and not replaced, then the probability that a king will be drawn given the first card is an ace is 4 out of 51. Notice here this is over 51. Typically, in a standard deck of cards, you have 52 cards. Since the ace was already taken out, we now have 51 cards, but clearly there are still 4 kings left. Again, giving us a probability of 4 out of 51. However, the probability of drawing another ace on the second draw, given that the first card was already an ace, will be 3 out of 51. This is known as conditional probability. The first event will affect the second. This leads us to the second multiplication rule. When two events are dependent, the probability of both occurring is the product of the probability of the first event and the conditional probability of the second event. It should be noted that if two events, A and B, are independent, then the probability of B, given that A has occurred, will just simply equal to the probability of B, since there is no change in the probability of event B, even though event A has already occurred. Again, this can only happen, though, when the events are independent. Here's an example of probability without replacement. Consider a standard deck of playing cards. 3 cards are drawn and not replaced. Find the probability of the following events. First, let's find the probability of drawing 3 tens in a row. I think most of us know that there are 4 tens in a standard deck of playing cards. The 10 of clubs, the 10 of spades, the 10 of hearts, and the 10 of diamonds. So drawing out the first 10 will clearly be a probability of 4 out of 52 cards. And since we're not replacing that 10 card back into the deck, there now are only 3 10s in the deck out of now 51 cards. And once again, since we're not replacing that 10 back into the deck, we now only have 2 10s out of 50. Multiplying those 3 probabilities will give us the probability of us drawing 3 10s out of a standard deck of playing cards, which in this case is approximately 0.0002. What's the probability of drawing a jack, then a queen, and then a king? Now these are different types of cards. And again, there are 4 jacks in a standard deck of playing cards, along with 4 queens and 4 kings. That said, the probability of us drawing a jack will be similar to the previous example, 4 out of 52. However, since now we're trying to find the probability of a queen out of the remaining cards, we still have 4 queens, but only 51 cards. So the probability of us drawing a queen, given that the jack was already drawn, is 4 out of 51. And finally, the probability that we would draw a king, given that 1 queen and 1 jack were already drawn, will be 4 out of 50. Once again, reducing, simplifying, and evaluating will approximately give us a probability of 0.0005. So this means that the probability of drawing a jack, then a queen, and then a king is a little bit higher than the probability of drawing 3 10s in a row. Drawing 3 hearts. In every standard deck of playing cards, there are 4 suits: hearts, spades, diamonds, and clubs. 52 divided by 4 is 13. Therefore, there are 13 hearts in every standard deck of playing cards. So to draw a first heart would be 13 out of 52. Again, there will be 13 hearts out of a total of 52 cards. Taking out the first heart means we have 12 hearts left now out of 51 cards. And finally, we have 11 cards left that are hearts out of 50. Reducing, multiplying, and evaluating gives us 0.0129. D. Drawing a heart first, a club second, and then a spade third. Again, these are all suits. A heart is a suit. There are 13 hearts in a deck. A club is a suit. There are 13 clubs in a deck. And a spade is a suit. There are 13 spades in a deck. So drawing a heart first will be 13 out of 52, just like the previous example. And now that I only have 51 cards, there's still 13 clubs in the deck. So the probability of drawing a club, given that a heart was already drawn, will be 13 out of 51. Then finally, there are now 50 cards in the deck, but still 13 spades. So the probability that a spade will be drawn, given that a heart and a club were already drawn, is 13 out of 50. Multiplying, simplifying, we end up with approximately 0.0166. Let's find the conditional probability of an event. Here, we're going to start to work a little bit backwards, using a formula from a previous slide. The conditional probability of an event B in relationship to an event A is the probability that event B occurs after event A has already occurred. That's what it means to be conditional. The formula for conditional probability is as follows. So in the event that they're asking you to find conditional probability, you need this formula here. Let's do an example. In a recent year, 0.99, that's 99% of the incarcerated population is adults. And 0.07, that's 7% of the incarcerated are female. If an incarcerated person is selected at random Find the probability that the person is a female given that, or after the fact of knowing that the person is an adult. Again, this is known as conditional probability. A big hint into conditional probability in a problem is the phrase given that. So the items that we know are event A, being an incarcerated adult, event B, being female. So the probability of being an incarcerated adult and female is 0.07. The probability of a randomly selected prisoner being an adult is 0.99. So the probability that the person is female, given that the person is already an adult, will be 0.07 divided by 0.99. In other words, probability of A and B divided by probability of just A. At a local country club, 73% of the members play bridge and swim. 82% of the members play bridge. If a member is selected at random, find the probability that the member swims, again, given that the member plays bridge. So what's given here is that the probability that a randomly selected person at a local country club plays bridge and swims is 0.73. The probability that a randomly selected individual at this local country club simply plays bridge is 0.82. So the randomly selected individual, who we already know plays bridge, what is the probability that they swim? In other words, what's the probability that the member we chose swims, given that we know the person plays bridge? Once again, you take the probability of them doing both divided by the probability of them just doing bridge. Here we get 0.8902. Probabilities for the phrase at least. The phrase at least is a very important phrase in any given statistics class, and the multiplication rules can be used with the complementary event rule to simplify solving probability problems involving the phrase at least. So if you're ever asked to find the probability of at least one occurring, then simply take 1, which represents the entire probability, 100%, and subtract the probability that none occur. And this should be somewhat familiar based on the complementary event rule we learned before. For example, of PhD students at a particular college, 60% have paid assistantships. If 3 students are selected at random, find the probability that at least one has a paid internship. So if we're looking for the probability that at least one of the 3 PhD students has a paid internship, we need to go ahead and use the complementary event rule as follows, which is 1 minus none of the PhD students has an assistantship. But first, before I can solve for this, I must note that they gave us that the probability that a PhD student has an assistantship is 0.6. And since the probability that a PhD student has an assistantship is 0.6, then the probability that a PhD student does not have an assistantship would be 1 minus 0.6, which would be 0.4. Therefore, the probability that none of the 3 PhD students has an assistantship will be 0.4 times 0.4 times 0.4, or better yet, 0.4 to the third power. In this case, we get 0.064. Now that we have all the information we need, we can now solve the probability they asked for. So again, let's find the probability that, again, at least one of the 3 PhD students has a paid assistantship. Simply take 1 and we subtract the probability that none of them have an assistantship, which in this case will be 1 minus the 0.4 raised to the third power, which is 0.064, we end up with 0.936. In a bouquet, there are 6 roses, 9 lilies, 7 daisies, and 6 orchids. If 4 flowers are selected at random and not replaced, so that would be conditional, let's find the following. Let's find the probability that, there's the phrase again, at least one of the flowers is a rose. And let's find the probability that all 4 are roses. Now, is either event likely to occur? Either event in the first part A or the event in the second part B? Be sure to show the steps that explain your answers. Let's start with the probability that at least one of the flowers is a rose. Once again, we need to use the complementary event rule. So here, the probability that at least one is a rose will be 1 minus the probability we have no roses. Now you'll notice we have 6 roses, and if I add up all of these flowers, we end up with 28 flowers total. So the probability that we have no roses would be 22 out of 28, because there are 28 flowers total, and there are 22 that are not roses. So the probability of me not choosing a rose in the first pick is 22 out of 28. Then picking the second flower, the probability that it's not a rose is 21 out of 27. And with those 2 roses gone, we now only have 26 flowers in the bouquet. So the probability that I don't choose a rose again will be 20 out of 26. And then finally 19 out of 25. Reducing, then solving, we end up with 1 minus 0.3573, which is 0.6427. Let's go ahead and find the probability that all 4 are roses. To do so, we take a look at the fact that we have 6 roses and 28 total flowers. So the probability that the first flower chosen is a rose will be 6 out of 28. And because we're not replacing it, the probability that the second rose is chosen next will be 5 out of 27. Because that's not being replaced, 2 are taken out, we now have 26 flowers left. We now have a probability of 4 out of 26 to pick a rose. And then finally 3 out of 25. Multiplying, simplifying, we end up with 0.0007. Is either event likely to occur? It is likely that the bouquet will have at least 1 rose. You notice that we had a fairly high probability, more than 50%. More than 50% means likely. But it is unlikely, in fact, very unlikely, that they will all be roses.